This is your presenter Asloob Mudassar, and I am presenting slide number 116 of the course on laser physics. Question is, in the beginning of laser invention, it was assumed that the lasers could operate only on a single longitudinal mode. Practically, multi-mode operation is possible. Find out appropriate reasons for multi-mode operation in the homogeneous and inhomogeneous cases. The answer is, the gain profile of a typical laser is quite broad and contains a large number of longitudinal modes separated in frequency by delta nu. And delta nu is equal to C over 2L, where capital L is the length of the cavity. The line width of a laser may contain a few to a few thousands of such modes when the transition is broadened by the Doppler effect. If the modes are well separated in frequency, the gain will differ from mode to mode. This gain difference becomes unnoticeable for modes around the central mode when the mode separation is small, or equivalently when the mode number is large. Thus, the modes around the central mode with high gain can also oscillate in the laser resonator. To have a broader view of the problem, let us discuss the plot of laser gain profile versus the frequency for different pump rates for homogeneous and inhomogeneous line broadenings shown respectively for TEM00 mode in the figure 1 and figure 2 respectively. That is, the homogeneous case will be shown in figure number 1 and the inhomogeneous case will be shown in figure number 2. And we are using the TEM00 mode, and the broadening that we are discussing in figure 1 and 2 are respectively homogeneous and inhomogeneous broadenings. For example, this is the case for the homogeneous line broadening. The caption of the figure 1 is plot of laser gain coefficients versus frequency for different pump rates under saturation condition for homogeneous line broadenings. So you see that the gain coefficient G, small g, is plotted along the vertical side, vertical axis, and the frequency nu is plotted along the horizontal axis. 3 consecutive modes have been shown, that is the mode at in the center, and the mode +1 mode on the right side, and the -1 mode on the left side of this central mode. So 3 modes have been shown, because we are assuming that at the moment 3 modes are oscillating in the cavity. So now we are presenting 3 different cases of the pump rate, and we are showing the corresponding gain coefficient profile. Let's start with pump rate 1, which is RP1, and we are assuming here the pump rate 1, RP1, is less than RP2, and you can see that the gain profile is shown, where we have labeled the central mode by M01, and the modes on either side of M01 are M11 and M-11. You can see that the gain of the profile is not very high when the pump rate RP1 is less than RP2. The next case, since RP2 is greater than RP1, but we are assuming that in the second case that RP2, that is the pump rate 2, is less than the critical pump rate. And here you can also notice the plot of the gain coefficient profile, which is higher in strength than the gain profile obtained with RP1, since RP2 is greater than RP1, but less than a critical pump rate. So you will notice that the profile is higher in strength than the profile which is due to RP1. So here we again labeling three modes here. The central mode is represented by M02, and the modes on the either side of this one are M12 and M-12. Now the third case that we are going to present is the RP3 pump rate. So RP3 pump rate is greater than the RP2 pump rate, and at the same time we are assuming that RP, that is the pump rate 3, is also greater or equal to the critical pump rate. That is, the third profile is applicable when the RP pump rate is equal to RC, that is the critical pump rate, or when the pump rate RP3 is greater than the critical pump rate. In both these conditions, the profile number 3 that we have drawn will be applicable. So this is the third one is the gain coefficient profile for the case when RP3, that is the pump rate 3, is greater or equal to the critical pump rate. So you can see that again we have shown by dot the central mode, which is labeled as M03, and the modes on either side of M03 mode have been labeled as M13 and M-13. So you see that with the pump rate is when the pump rate is increased, the gain profile shift upwards. That is, each mode has more probability and higher probability, and the strength of each mode, each of the three modes will be enhanced. Now you see that we have not shown the loss line over here. That is because the losses are occurring in the laser cavity, and we have not shown the loss line over here. But suppose that if your loss line is above the M02 level and below the M13 and M-13 levels, for example, the dotted line due to the loss is passing like that. That is below the M13, M-13 levels, but above the M02 levels, then of course only the three modes, that is M03, M13 and M-13 would be able to oscillate when the pump rate RP3 is greater or equal to the critical pump rate. Otherwise, no modes will be oscillating in the cavity. Because here if we assume that our loss line is greater than the M02 pump rate, then you see that the no oscillations will occur in the cavity due to RP1 and RP2, because their maximum value of modes, for example M02, will be lying below the below the overall loss in the cavity. So this is what our assumptions that we are making over here. So now let's read the paragraph, relevant paragraph, to see the detail about the description of figure number 1. For homogeneous case, three curves for three different pump rates, that is RP1 is less than RP2, RP2 is less than critical pump rate, and pump rate 3 is greater and equal to RCP, that's the critical pump rate, are shown in figure 1. So we have shown three different pump rates and the corresponding three different curves for due to these three pump rates are shown in figure number 1. The curves follow a similar trend as the case is homogeneous. That is the three gain coefficient profiles for the three cases follow similar trend because of the homogeneous line broadenings. The central mode starts oscillation first when the inversion, which is given by capital N is equal to N2 minus N2. These are the population in the two levels of the laser. That is, N2 is the population in the higher laser level and N1 is the population in the lower laser level, and the difference is designated by capital N, which stands as the population inversion. The central mode starts oscillation first when the inversion, which is capital N, reaches a critical value NC. NC is the critical value for population when the gain becomes equal to the cavity losses. So you see that at the critical value of NC, the two, that is the gain and the cavity losses, becomes equal to each other. This corresponds to the pumping rate equal to RCP. When the pumping increases beyond the threshold value, which is the RCP value, critical pump rate, the critical pump rate value, the inversion stays constant, equal to its steady state value NC. The gain of the central mode M03 remains fixed for RP3 is greater than equal to RCP. In fact, the whole gain profile remains fixed. That is, the gain of the other modes M-13 and M+13 also remain fixed and remain lower than the central mode. If all the modes suffer through the same loss, then only the central mode will oscillate under the steady state condition. So you see that in this case, in principle, only the central mode should oscillate, because the gain, because as we assume that at the critical pump rate, the gain and the losses becomes equal to each other. So when the pumping 3 becomes greater than the critical pump rate, the population inversion stays constant. So the M3 values also stays constant, but due to enhanced pumping rate of P3 beyond the value of the critical pump, the M03 first oscillates in the cavity. So if the cavity losses becomes lower than the M13 and M-13 modes, then of course these three modes will also start oscillating in the cavity. And you know that we are only discussing one pump rate at a time. That is, either we are discussing RP3 or RP2 or RP1. So at least one of these pumps will be considered. Since the lasing action will be only possible when RP3 is greater than equal to RCP, that is the critical pump rate. Under this condition, only the modes will oscillate and a laser with these modes can come out of the laser cavity. But you see that if we are pumping with RP2 and RP1, which is smaller than the critical pump rate, no oscillations will take place outside the laser cavity. In the inhomogeneous case, the transition frequencies of the individual atoms. So here, be very careful. That is, you see that in the homogeneous broadening, all the atoms are for example, if they all the atoms either oscillating, or either emitting, or either resonating at the frequency corresponding to M03 mode, or resonating at M13 mode, or resonating at a frequency which corresponds to M-13 mode. So three resonant frequencies will be present for the homogeneous case in the case that we have shown for the RP3 greater than equal to RCP. So three modes mean that three resonant frequencies are present in the laser cavity. So all the atoms are either resonating at a frequency corresponding to M03 mode, or corresponding to M13 mode, or corresponding to the resonant frequency corresponding to the M-13 modes. So no other frequencies are present. But you see then in the inhomogeneous case, since this is the inhomogeneous case, it means that each atom is individually oscillating at a frequency, and that their resonance frequency may not be equal with others. So in the inhomogeneous case, the transition frequencies of the individual atoms are distributed over the spectral range, and the cross section is the superposition of the cross section of the individual atoms. So you see that when the stimulated emission will take place, and then of course there will be an addition or the superposition of all the individual atoms of all the cross sections due to the individual atoms. This leads to spectral hole burning in the gain curve, as shown in figure number 2. So notice we are talking about the spectral hole burning in the gain curve. So the gain curve corresponding to the inhomogeneous case is shown in figure number 2. The caption of the figure states that plot of laser gain coefficient versus the frequency for different pump rates under the saturation condition for the inhomogeneous line broadening. So the separation between the modes is C over 2L. So we have again shown the three modes so that we can make a comparison with the modes in the homogeneous case. So you see that the first case is RP1 when the pump rate 1 is less than the critical pump rate. You can notice that the gain profile look like this one. Again, there will be three. You see that now we cannot say that there will be three modes of there because there could be many modes oscillating due to the inhomogeneous broadening. But we have shown only the position of the three modes at the bottom. But many modes are present, could be present corresponding to the gain profile. So when the RP2 is equal to the critical pump rate, then you will notice the gain profile is going like this one. This is the gain profile when the pump rate P2 is equal to the critical pump rate. But if you increase the and you see that here I have drawn the loss line. So the loss line matches with the top, which matches with the central mode of the pump rate 2 under the pump rate 2 RP2. So the curve corresponding to RP2 again have many modes and the loss line has been shown corresponding to the top mode or corresponding to the central mode. And if the RP3, if the pump rate is RP3 is increased beyond the value of the critical pump rate, then of course you will notice that a special that is a spectral hole burning will be prominent. So you can see that the spectral hole burning is over here. The spectral hole burning is shown over here, and the spectral hole burning is shown over here. Corresponding to the central mode, the spectral hole burning is also symmetric. That is the modes, that is the value of the mode in the center will stay the same at the loss value, and the other modes will increase beyond the value of the central mode. So these are the modes which are lying in this region and which are lying in this region. They have gained the values greater than the value of the central mode. And you see that these modes are also higher in the central mode and they are oscillating. But here you see that the hole burning has taken place. And you will see that this particular mode is also oscillating at the mode corresponding to its loss value. And similarly, the mode plus 1 also. So many modes are oscillating in this region, and when the hole burning occurs, for example, corresponding to the plus 1 mode, you will notice that this mode will then be oscillating at its original values, which corresponding to the values of the loss. So the spectral hole burning will appear. It means that some modes can gain a value greater than the value of their corresponding modes, of their modes corresponding to the modes that we have shown for the case of the homogeneous case. And many modes can take a value greater than the values of these modes. But of course, at some modes when the hole burning will take place, then for such modes where the hole burning takes place, the minimum of such modes will then be oscillating at a value of the loss. That is, they are produced and lost in the cavity, and they are not oscillating out of the laser cavity. But those which have a value greater than the value of the loss will be oscillating in the laser cavity. The description of the figure is here. When RP increases beyond the critical pump rate, that is RP3 becomes greater than the critical pump rate, the gain of the central mode stays fixed to its critical value. That is this central mode. The gain of the central mode stays to its critical value corresponding to the critical pump rate. The gain of the central mode stays fixed to its critical value, whereas the gain of the other modes keep on increasing till they reach the threshold value. Thus, under the condition that RB3 is greater than RCP, more than one modes can oscillate. So you see that there is a possibility that many modes present over here and present over here, except the region where the hole burning has taken place. These modes have gain their values greater than the central mode, and they can oscillate within the laser cavity. So more than one mode can oscillate in case of the inhomogeneous case. The above analysis establishes that only the central mode oscillates in the homogeneous case, but the actual findings are different. That is, multi-mode oscillations occur not only for the inhomogeneous case, but also for the homogeneous case. So you see that if our gain curve is lying above the M13 and M-13 level, only the central mode will operate for the homogeneous case. But principally, we have found that the mode 13 and -13 are also lying above the loss line. And so the three modes, at least in this picture, the three modes will oscillate within the laser cavity. In principle, if this gain curve is much broader than, of course, the other modes, because if this gain curve is much broader than the separation between the modes, which is C over 2L, and many other modes can also oscillate within the laser cavity. So multi-mode operation is also possible for the case of homogeneous line broadening. Consider two consecutive modes, the central mode and the mode next to the central mode. For example, maybe the mode lying on the right of the central mode. The two modes have well-defined standing wave patterns. You know that each mode will only exist and would be able to oscillate within the resonator and will contribute in the output laser power when the standing waves are established. The two modes have well-defined standing wave patterns between the resonator mirrors. Resonator mirrors and through the active medium. So you see that in the resonator, when the two standing waves are set up, that is the minimum values of the electric field of the standing waves lying on the mirror number 1 and the mirror number 2, then they differ in wavelength. That is, they differ in wavelength by lambda by 2, and this difference appears as a shift of lambda by 4 in the active medium region as shown in figure number 3. So you see that the two modes, that the two consecutive modes, for example, one mode is in the center, the other mode, for example, on the right side of this one. For example, if the central mode is operating, for example, M03 is operating at a wavelength lambda, then M13 will be operating at a wavelength lambda plus lambda by 2. Because of the difference in C over 2 L is the separation between the two modes. So this is the frequency separation. So under that condition, when there will be a shift of lambda by 2 of the second mode with respect to the first mode, then actually this difference of lambda by 2 appears as a shift of lambda by 4 in the active medium region as shown in figure number 3. For example, over here, I have not shown the mirror 1 and mirror 2 because in the mirror, if there are two mirrors around the active medium, then of course the standing waves will have a minimum value like the value shown in at the point A in the active medium. That point will also coincide with mirror number 1, and similarly a minimum electric field value will also coincide with mirror 2 on the right hand side. That is, the minimum of the standing wave pattern will occur at mirror 1 and mirror 2 due to each of the mode 1 and mode 2. That is, the mode 1 and mode 2 will have their minimum of the standing wave patterns coinciding with mirror 1 and mirror 2. But in the active medium, you will notice that there will be a shift of lambda by 4. in the standing wave patterns. For example, the mode 1 is shown by the solid line, and we have shown the 3 points A, B, and C where the electric field is 0 for the standing waves of mode 1. And consider the second mode with a dotted line. This mode has suffered a phase of suffered a shift of lambda by 4 with respect to the standing wave pattern of mode 1 only within the active region, active medium region. So let me read the caption 3. Caption of figure 3. Standing wave pattern of two consecutive modes in the active medium region, which is shown in the top figure, and the spatial hole burning pattern for population inversion due to mode 1, that is the bottom figure. So in the bottom figure, the spatial hole burning pattern of the population inversion is shown. So you see that here we are plotting the population inversion n as a function of z. And you see that the z-axis is actually the axis that we have taken along the axis of the active medium rod. So this z-axis, for example, z has a value equal to 0 at the mirror 1, and the value of z increases towards the mirror 2. So here we are plotting the value of the population inversion within the active medium rod. You will see that the population inversion oscillates sinusoidally. That is, for example, it is population inversion is maximum, then of course it goes to a minimum value 0. The population inversion becomes 0 over here, not 0, a slightly greater than 0, because the 0 line is over here. Some population, but smaller population, not enough population. So this population inversion will increase along the value of z, then reaches the top value. Then further, when you move further along the value of z, the population inversion will decrease and reaches to the minimum value. This minimum value is well above the value of the zero level. That is, the population is not going to be 0. It has already some value some value, but you see that the values are oscillating. So the hole burning. So this is the population corresponding to the hole burning, spatial hole burning. The spatial hole burning corresponds to the value where the population is minimum. So due to this minimum value, we can say that the spatial hole burning of the population inversion takes place where the population is where the population inversion is minimum. So these are the points corresponding to the spatial hole burning in the population inversion. So the population inversion will also oscillate sinusoidally as you go along the z-axis or along the active medium rod. So it is not uniform along the active medium, but it is also fluctuating, that is fluctuating between the maximum and minimum value in a sinusoidal manner. The zeros of electric field, that is A point, B point, and C points. For example, these points A, B, C. In the standing, the zeros of the electric field ABC points in the standing wave pattern of mode 1 do not use up the inversion. So ABC are the points where the standing wave in the standing wave pattern of mode 1 where the inversion is not used. So the zeros of the electric field in the standing wave pattern of mode 1 do not use up the inversion, because the electric field is minimum there, and the population which is present over there will stays unused, which continuously grows where the inversion is depleted at points where the electric field is non-zero. So the inversion is depleted at the points where the electric field is non-zero. So these are the points between A and B, where if you go from point A towards the value in the standing waves, the electric field is increasing over here, reaches to the maximum value, and then of course it will decrease towards the point B. So these are the maximum values where the population inversion is depleted. So this is the region where the population inversion is depleted. And A, B, and C are the points where the population inversion remains unused. So the zeros of the electric field corresponding to the A, B, C points in the standing wave pattern of mode 1 do not use up the inversion, which continuously grows where the inversion is depleted at points where the electric field is non-zero. The gain of mode 2 increases with the increase in pump rate as it uses the inversion left undepleted by the mode 1. So you can see that the points, that is A, B, and C points, for example, corresponding to mode 1 where the population is undepleted, and this population will be used by the mode 2, because you see that where the minimum of B occurs, there is a maximum of the electric field in mode number 2. So it means that the mode number 2 will use the population left by the mode number 1 unused. So the mode 2 will use the population left by the mode number 1 which is unused. That population will be used up by the mode 2, and this population is actually the population inversion. So the gain of mode 2 increases with increase in pump rate as it uses the inversion, that is it uses the population inversion left undepleted by the mode 1. Thus at large pump rates well above the threshold, mode 2 can set up into oscillation. The oscillation will set up when the gain becomes equal to the losses. We may conclude that the multi-mode operations in the homogeneous and inhomogeneous cases are due to hole burning in the spatial distribution of inversion and the hole burning in the spectral distribution respectively. That is, for the homogeneous case, the multi-mode operation can be associated with the hole burning in the spatial distribution in inversion, where the inversion sometimes is not used by mode 1, for example at the points where the minimum, where the population inversion is unused and that population inversion is used up by the second mode. So similarly, following a similar pattern, the multi-mode operation can exist in the homogeneous case, and similarly for the inhomogeneous case the multi-mode operations can exist due to hole burning in spectral distribution. Modes in the inhomogeneous case are well separated in frequency from each other, and their oscillations do not depend on spatial hole burning of inversion. Oscillating modes in the homogeneous case are smaller in number than those in the inhomogeneous case because the spatial variation in inversion is wiped out if more modes are present, and as in case of the inhomogeneous case, if more modes are present, then of course the spatial variation in inversion is wiped out. So you see that we have tried to explain how multi-mode operation can occur in the case of homogeneous and inhomogeneous line broadenings. So this is the end of slide number 116.